Hi guys, let's do reachable nodes with restrictions. So we're given an undirected tree with n nodes labeled from 0 to n minus 1 and n minus 1 edges. And we're given a 2D integer array called edges of length n minus 1 where edges at I equals a at I comma b at I indicates that there's an edge between nodes a at I and b of I in the tree. And we're also given an integer array called restricted, which represents restricted nodes. So they want us to return the maximum number of nodes we can reach from node 0 without visiting a restricted node. So note that node 0 will not be a restricted node. So if we take a look at example 1, we have 7 nodes here. We're given this array of edges in our input here, okay? And our restricted array is this, which is nodes 4 and 5, so they marked those red here. And we would output 4 because from node 0, if we start here, we can visit 4 nodes, which is 0, 1, 2, and 3. So that's 4 nodes. And we cannot get to 6 because to get to 6, we would have to go through a restricted node, which is node 5, and we can't go through here. So this also doesn't count, and we can't visit node 4, so these are all blocked off. Okay, and then in example 2, we're given this tree, and we have n equals 7. There's 7 nodes, 1, 2, 3, 4, 5, 6, 7. And we're given this array of edges, and these nodes are restricted. So 4, 2, and 1 are restricted nodes, which are red. So we can visit 3 nodes, which are nodes 0, 5, and 6, which are green. And we can't get to 1, 2, 3, or 4. We can't get to 3 because we would have to get through 2 to get there, and we can't visit 2 because it's restricted. So yeah, basically, well, first things first, we're given an array of edges, which, as we know by now, is not a convenient format to use. So the first thing we're going to want to do is convert this array of edges into a hash map that maps each node to its neighbors. That way we have O of 1 lookup when we're trying to visit a node's neighbors. And then also, we are going to want to traverse this tree starting from node 0 with either a DFS or BFS. And we can use our hash map of nodes and neighbors to visit each of the neighbors of a node. And then we also will want to keep a set to keep track of all of the nodes that we've already visited so that we don't end up with any endless loops. And lastly, we are given this array of restricted nodes. And I'm actually going to want to convert that into a set for O of 1 lookup time. Because in array, to check if it contains an element, we're going to have to loop through the entire array every time we do that, which is O of n time, which is terrible. So converting it into a set will allow us to just do that in O of 1, which is much better. And it doesn't really matter for space, honestly, because our hash map is already going to take up more space than the set would anyway. So it's honestly not that big of a deal. So, okay, let's start out by setting up our map. So I'm going to do map of integer list integer. Okay, graph equals new hash map. And then this will start out as empty. Okay, and then we're gonna loop through our edges. And for every node that we encounter, so like I'm gonna loop through each inner array in here actually, and do a for each loop. That way we can just access the elements by saying like edge at 0, edge at 1 for the, because each of these is like of size 2, right? So for int array edge in edges, we're going to put if absent this key 0 with an empty list. Okay, so what that's going to do, we're going to start off with like first edge is going to equal this. Okay, so currently edge equals this array, and edge at 0 is in this one because this is index 0 right here. we do not have this key in the map or graph or whatever so far. So we're going to add that with an empty array list, okay? And then we're going to want to do the same thing for 1 because this is undirected. So any edge here is going to go both ways, from 0 to 1 and from 1 to 0, okay? So we're also going to do that for 1 and an empty array list. So then we will also have this now. And then we're going to want to add the element into the list for each one. So dot get edge at 0, dot add edge at 1. That's going to add this 1 in here. And same thing for the other one. Okay, so that's going to set up our graph here. So like this is going to have a 0. And then if we loop through the rest of it, just so I can show you guys, you can skip ahead if you already know what this is going to do. But then edge will be this. We already have 1, so we don't add 1 again. But we don't have 2, so we're going to add the key 2 with an empty list. And then we're going to add edge at 0 is 1. So for the element at 1, we're going to add 2 into the list. And for 2, we are going to add 1. So then like that. Okay, and then I feel like you guys already know how this works, so we will just add the rest of these. So for the next one, we're going to add 3. Okay, and that eventually it's going to have a 1, and then for 1, we're going to add 3. For this one, we're going to map 0 to 4, and we're going to map 4 to 0, 0 to 5, and 5 to 0. And 5 to 6, and 6 to 5. Okay, so that's going to be our final graph here once we've looped through the entire array. And then once we've looped through the entire array, then we exit this loop and we're done with our graph, as we can see. Okay, and then next thing we're going to want to do is convert this restricted array into a set. So let's initialize a set. I'm going to call it restricted set. Okay, and then we're just going to loop through everything in here and add it to the set basically. So for int r in restricted set dot add r. Okay, and then now our set is just going to look like, so like let's say, just use example 1 because that's what I did for this one. Let's say restricted set equals this. Well, now let's say our array is that, then restricted set will just contain that, okay? And I guess I usually just do that for set. So you can tell it's like different than an array. Okay, so that's done. And then we will want to now set everything up for our DFS. So first we're going to need a set to keep track of our visited nodes. So set integer visited is new hash set. Okay, and that is empty. Okay, and then we are just going to return a DFS on this node 0. So return DFS 0. We're going to pass in 0, okay, to start, because that's the node that we're starting at. And we will want to pass in our graph to be able to visit the neighbors, because if we start at 0, then we need to be able to visit all of 0's neighbors, right, which is this, so we need to access that through the graph. We also need visited, because that's how we'll exit our DFS, is if we've already seen a node, then we don't want to revisit it, okay? We also want to pass in our restricted set, because if it's in our restricted set, we're not going to explore that node, okay? So let's say our restricted set is 4 or 5. Well, if we're at node 0 and we're exploring 0's neighbors, we're actually only going to explore 1. We can't explore 4 and 5 because these are restricted. So we'll skip over these if it's in the restricted set. So that's how that's going to work. Okay, now let's make our method for our DFS, so private int DFS. Gonna take in an int node, map integer, list integer, graph, set integers visited, and our set of restricted set. Okay, sorry about that. Like, my screen's a little bit cut off at the end, so it's like really hard for me to see sometimes, like when the lines get really long. Okay, and then how we know we're gonna exit our DFS is if, okay, well, two cases. First of all, if we've already seen that node, then we're not gonna revisit it. So if visited contains node. The other possibility is that it's a restricted node. So, or restricted set contains node. Then we'll exit and return 0, okay? Because we're going to return, basically in our DFS, like let's pretend there's only one node, okay? Let's just say there's node 0 and like nothing else besides 0. Then we would return 1 because that's one node that we can visit, right? So if we visit node 4, that's a restricted node, we can't actually visit it, we would return 0. Like it's not contributing to the total amount of nodes that we can visit. So 1 if it is contributing, 0 if it's not contributing. So we would return 0 in this case because it's not contributing to the total node count. So if not, so we can visit this node, then we will add it to our visited set. So add node. Then we will want to loop through all of its neighbors and do a DFS on that. So first of all, well, okay, let's keep track of how many nodes we can visit. So we're gonna create a variable for that called, let's just call it count. We'll set it to 1, okay, because we have visited our current node, which is 1. Okay, and then we're going to loop through its neighbors. So for int neighbor in graph.getNode, because if we look back up here, graph.getNode, let's say we're at node 0, right? Graph.getZero is going to give us this list of neighbors. So we're basically looping through all of these neighbors and doing a DFS on these ones. So next we're going to visit 1, and then here's 1. We'll add 1 to our visited, and then we'll go through 1's neighbors, which is this, and so on, so on. And then 0, we already visited that, so we'll skip it. Then we'll go to 2, and then 2, its only neighbor is 1, so we actually skip that because we've already seen it. We'll go back to 1, and then since we already saw 2, we'll go to 3. Then 3's only neighbor is 1, so we skip that, and then we backtrack basically, and then we're at 4. And then 4 is restricted, so we skip that, and then we go to 5, and 5 is restricted, so we skip that, and then that's it. We're done with the entire traversal, and then whatever count we got, so we visited 1, or we visited 0 technically, so that counts as 1, then we visited 1, which counts as 2. Then in 1, we visited 2, so that counts as 3, and then we went back to 1, so that doesn't count as anything, and then 3, so we went to 3, and then that counts as 4, and then we went back to 1, and then this is done, and then we went back to 0, and these are restricted, so then we end up with 4, and as we can see, the output's 4, so that's how this works, okay. Then basically for every neighbor, we are going to add to the count, so plus equals DFS, neighbor, and then just pass in everything that we're passing in. So the only difference is that we're doing it on the neighbor here instead of the node, okay? And then we're just gonna return the count. Yay, okay. Sorry if I seem really dead, guys. Like today was a long day, but I still wanted to get a video out, so. Okay, the time complexity here is O of n plus e, where n is the number of nodes in the tree or graph or whatever you want to call this. Technically a tree, but undirected, I guess. E is number of edges. Okay, before I move on, let me explain this. So if we think about the algorithm here, we're starting at node 0, right? And we are visiting as many nodes as we can from node 0. So either, okay, let me back up. So like, I guess worst case, right? Our worst case possibility is that every single node is green. So there's no restricted nodes. And if that's the case, then we are visiting every single node in every single edge, right? And so that gives us O of n plus e, basically. And then if we take a look at the algorithm, or like the code, I mean, here when we are building out our hash map, our graph, right, of nodes to edges, we are processing every single edge here once. So like for example, from 0 to 1 and from 1 to 0, right? And so on. So like every single edge is getting processed once here, so that's O of e in here. And then every single, okay, this is like worst case, I guess, O of n, but it doesn't really matter because like, well, okay, like, yeah, I guess if every single node was restricted somehow, this would be O of n, but that would be kind of weird. But basically, like, I guess the O of n really comes from this DFS because, like, let's say no nodes are restricted, then we are, worst case, visiting every single node, and that's going to be O of n. So then we get O of n plus e, basically, in the end. Okay, for time. Then for space, we are also going to have O of n plus e. And so if we take a look at our code here, we have this hash map, which is mapping every single node to every single edge. So that already is O of n plus e, since we're storing every node and every edge. Yeah, and then we have this restricted set, which is worst case O of n if somehow every single node is restricted. Though again, that'd be kind of weird. And then our visited set is storing O of n. I guess, okay, worst case, if none of them were restricted, then this would be O of n, like it would store every single node. But I guess you could say like it's up to O of n. And then in the DFS call stack, then we also, worst case, have O of n if every single node is green. And, well, I guess, okay, it wouldn't actually be because, like, unless, like, every single node was, like, in a line, then this call stack would be O of n. But regardless, like, it's still O of n, worst case, but that's just, like, the breakdown. So yeah, we get O of n plus e because the hash map kind of just like overrides everything since this is already O of n plus e by itself. So yeah, that's it for this video. Thank you guys for watching, and like and subscribe if you found it helpful. Bye!